let's see, is it recording? Yes. All right, so I do have a few kind of small announcements to make that might, be important. I did put up on Blackboard and I sent an announcement, I think, but hopefully you got that. Basically, I put a little practice test on Blackboard so that you can try using the Respondus lockdown browser. You want to make sure you do that before Friday so that if you have any technological problems, you can figure out what they are and address them. So it really just, once you get the lockdown browser installed, taking this test will take you maybe 2 minutes. So it's just to let you practice. If you've never done the Respondus lockdown browser in particular, make sure you do it so you see how it works. But I'll just give you a quick overview. You're gonna log in. You're gonna open up Respondus lockdown browser, which you have installed on your computer, and then you will go into Blackboard. You'll go into course content. There's an exams folder, and you'll open that up, and you will see actually the practice test. The practice test is just in the content. It's just right in front, so you'll see it. You'll go to start it. It's going to say, it's going to ask you to take your picture. It's going to ask you to show your ID and take a picture of that. It's going to ask you to give like a short video clip just to make sure it's able to pick up your audio and process the video, whatever it's doing. And then you'll start, and it's going to show you the test, and there are 3 questions on this test. And the first 2 you type in response, and the third is going to be a file upload. So you want to make sure you can do all 3 of those things, and if you can, you'll be in good shape for this upcoming exam. When we do the real exam, it's going to appear in the exam folder, and it will appear at the time that the test starts at 11. So it won't appear before, but you'll go through that same process with the Respondus lockdown browser. And what I'm going to do with that, and I'll make this kind of explicit when you're taking the test, but I'll kind of inform you now, is you're going to see the whole test at once. And each problem, you're going to just put your answer into Blackboard when you're taking the test with Respondus. You will not, I don't think it's very easy to upload your work while Respondus is locking out your computer. So you're going to put just your answers, and after you complete the test, there's going to be a separate test in that folder that appears, which it doesn't use Respondus, but you just click it and you can upload pictures of your test. So if you want partial credit, okay, so that I can give you partial credit on your work. You do need to upload that so I can see your work, even if you don't want partial credit. So I shouldn't have phrased it that way. You'll upload pictures of your work, and I'll create a document that tells you kind of what you need to do. But essentially, I would like the pictures to be either a zipped file of JPEGs, so you can have a zip file of JPEGs and upload it, or you can put them into a PDF. So to get them in a PDF, you could drag your pictures into a Word document and save as a PDF, or there's different ways. So if you don't know how to do that, let me know, and I'll try to talk to you individually, like what technology you have. But one of those 2 options is what I would like. It needs to be a single file because that's how Blackboard accepts the upload. And then also make sure your images are not sideways. Rotate them before you send them to me. Otherwise, it winds up taking me hours and hours and hours to fix everyone's images. So if you each fix your own images, it only takes you a minute or 2 to make sure that they're upright. And also, please make sure your images are not huge in terms of file size, because then it takes me a long time to download them. And then when I return them to you graded, it takes a long time to upload. And it's not like you're taking a picture of the Grand Canyon or something. You need like 20 megapixel image. Just take the smallest image size you can, and that will be plenty big enough for me to grade your test. Grace.
Will our work be due within that test time too? Like, should we try to
No, so I'm going to give a certain time interval from the time you complete Respondus before you upload um, the copies. I'm thinking like 15 minutes should be sufficient for you to take pictures. But I'm open to feedback if you guys think that that's not feasible. Let me know. I'd like to try that for the first contest and see how that works. So, you submit your test at 12:42 or something. So then you have 15 minutes from that time to upload your pics of your work. And if that proves because of technological problems it takes you a little longer, we can try to figure that out. Okay, so great. Any other questions about that? Okay. Go ahead and take that test sooner rather than later. That way, if there are questions, if you find out you're having some real trouble, then we can try to address it, before Friday. Additionally, under course content, and I think you'll find it at the bottom, I think it's on both classes. I'll make sure after class, but I added an equation sheet for the first contest. Sorry, I call the test contest. So if you hear me saying contest, that's a test. Okay, I'm going to slip into that language from time to time because I don't know, that's my habit. But there's an equation sheet for the contest, and you don't need to print sheet or anything. It's going to be on the contest when you take it, so you'll be able to see it during the contest on your screen. But I thought some of you might like to see it beforehand when you're working on homework. If you kind of work with that equation sheet, then you kind of know what you have. And then this equation sheet's pretty minimal because it's the first chapter, but as we go in the semester, we get more and more equations. And so, having access to those equation sheets and knowing where everything is organized will help you when you're actually taking the contest. Okay, so, have a look at that. But you don't have to do anything special with it. That's for information only. Any questions about the sheet? Okay, so let me get the whiteboard up and do a quick kind of refresher what we were talking about last time. Okay, so basically, let me see if I have the right pen. So we were doing graphs, and we were doing graphs of position versus time. And our graph could have straight lines, segments, it could do anything, really. And what we saw is that from looking at the graph, the height on the graph is indicating the position. The horizontal direction is at what time that position occurs. And then we can furthermore see the velocity by looking at the slope. So, if we, for example, look at a straight line segment, then it's really clear. The slope of that line is just the velocity. We would say the average velocity is delta x over delta t, which would be rise over run. If you have a curved segment, on the other hand, calculating rise over run depends on which 2 points we pick. And so we defined this concept called instantaneous velocity. And so maybe we pick a point like that, and we draw a straight line that's tangent to that curve. And that straight line, then the slope of that line gives us the instantaneous velocity. Some of you have been doing homework already, which is great, and have asked questions because there's at least one problem where you're supposed to do that and find the instantaneous velocity at a point. And when you do that, you may get a slightly different answer from the book. And that's fine, because it's not an exact science drawing a tangent line. I mean, technically there should be an exact thing, but practically speaking, you can't do it. And I'm really mostly interested in that you understand that concept, that the slope of the tangent line tells you the velocity, rather than that you can very precisely and accurately get the same answer that I get. Okay, so if I get a slope of this thing of 0.9 and you get a slope of 1, those are both just as good. from my perspective. Okay, so any questions about that? That's kind of a quick reminder what we had been talking about. Okay, so today we're going to learn, and we also, I should remind you, we defined acceleration, the average acceleration, which is change in v over change in t. But the key thing here is that we can tell the sign of the acceleration if it's positive or negative. And how do we know if the acceleration is positive from looking at a graph?
It's positive if it goes up and to the right.
Not necessarily. Not necessarily. The slope is positive, so if we're talking velocity, then the velocity is positive if it goes up and to the right. But for acceleration, we're looking for a different feature of the graph. Anyone else have an idea? Isabel?
We talked about how when the graph, like when it's positive, it makes like a smiley face.
Exactly.
When it's negative, it makes a smiley face.
If it's happy or sad, that's right. And if it's neither happy nor sad, then it's neither positive nor negative, which means it's zero. So in most of this graph that I drew, there's no acceleration at all, but in this particular window, there is an acceleration, and the acceleration would be positive because it's happy. Okay, so that's kind of what I'm looking for. And I know saying happy or sad sounds kind of, simplistic, but I think it's really good for remembering, how that works. Okay, so today we are going to start learning we're going to learn essentially two things. We're going to learn how to create some equations that will help us solve problems, and then we're going to start solving problems with the key focus being how do we interpret word problems, because in my experience, students in this class usually can solve the algebra, but it's knowing like what exactly you're supposed to be doing that is the problem. So when we read a question in English, if we knew which equation we're solving, it's fine, but the question is which equation sort of relates to that English. And so we're going to spend a lot of time on that today. But before that we do that, we need to get some equations. So let's start with our definition of acceleration. So acceleration, this is technically the average acceleration. It's delta v over delta t. And as I said yesterday, may have slipped past, but we're really only going to be talking about constant acceleration in this class. If we have a situation where the acceleration is not constant, we will not be able to use all of these equations that I'm going to derive, but we will have learned new tools by that point. So I'm not going to write a bar over the acceleration to indicate average all the time. So I'm just going to go ahead and get rid of that now. And from now on, A, when we see A, unless it's otherwise mentioned, it's just a number, okay? It's not a changing quantity, it's just some number, some constant number. So what we're going to do is we're going to rearrange this, and we're going to find an equation for VFinal, for the final velocity, by using the definition of acceleration. So VFinal is going to appear inside of the delta V. So delta V, remember, stands for change in velocity. And a change in something is always the final minus the initial of that something. So for example, if you wanted to find your change in weight since the beginning of the pandemic, you would take your final weight, your weight today, and your initial weight at the beginning of the pandemic, and you would subtract the final minus the initial. And I recommend you don't do that. It's not worth thinking about. But final minus initial always, not initial minus final. So we could say that the acceleration is v final minus v initial over, technically this should be t final, minus t initial. But we're going to a little bit of a cheat in this class, and we're going to say that 99% of the time we're going to say that the initial time is just 0. That is, we got some experiment and we just start our stopwatch, we start recording video footage and we start the time on the clock at 0. So if we do that, then we really only have t final on the bottom. And to simplify things further, we're just going to call t final, we're just going to call it t. Okay, so the time t, the variable t, is always our final time. So this equation then becomes a equals v final minus v initial over t. Okay, so what I'm doing, I'm starting with the definition of acceleration, and I'm kind of changing the variables and making some rules a little bit to create an equation. And once we have that equation, we'll talk about what each variable means and how to interpret it. But that will be then the final, equation that we use. We won't really go back to definition of acceleration a lot. We kind of are using that as a tool to get to a final equation. Now, what I would like to do is I would like to solve this whole thing for v final. And in algebra class, you solve stuff like this all the time, but it looks a little different from how it looks in physics class, because in algebra class, the v final would just be x. And the other stuff in this equation would probably be numbers. It might look something like x minus 2 over 3 equals 4, and you want to solve this thing for x. Okay, and if we all see this in math class, everyone in this classroom can solve this and find out what x is. We're going to start out by multiplying by 3 on both sides. We get 12 equals x minus 2. And then we're going to add 2 to both sides and get 14 equals x. And if I made this your first problem on your first test, you'd be so happy. You'd be like, yes. But when we see it in physics, it's all symbols. So this makes us it makes you at first as a student feel a little uncomfortable. It just feels nervous, like there's all these symbols and it's hard to look at it. It's almost, you get worried looking at it. But the steps are always the same. And so for the first several weeks, we're going to be working with these symbols and it's going to be hard. And you're going to have, when you solve problems, a temptation to plug numbers in for v initial, time, and acceleration so that it looks like this, and then solve it like you would in math class. And I'm going to urge you, encourage you, insist that we don't do that, that we instead do the algebra steps first and plug in later. And the reason for that is we need to get better at visually scanning equations full of symbols, because sometimes we won't have numbers. And if we're overly reliant upon plugging numbers in first before we do the algebra, we will hit a wall about a month into the semester, and then we will find what should be easy becomes incredibly hard. So for this first kind of month, we're going to be doing what seems unnecessary, okay? That is solving the algebra with just symbols. It's really like we're working out, our brain. We're doing a workout to get sort of the algebra part of our brain stronger, so that when we get to new things, they're easy tasks instead of hard tasks. So I probably talked too much about that, and I'm going to talk about it again. But what would be the first step if I want to try to solve this for v final? What's the first thing I really need to do? Anyone? Wyatt.
You would multiply both sides by t.
Yeah, we want to multiply both sides by t because, first of all, we don't like fractions, right? Almost nobody really likes fractions. It's easier to do algebra when we don't have a denominator. So we just get rid of that denominator. We're going to multiply by t over here, and we're going to multiply by t over there. And when we do that, on the right-hand side, the t's just cancel. And on the left-hand side, we might just write this as at. So we don't need a an asterisk or a time symbol. I don't like to use an X for multiplication because we have X for variables a lot. But we don't even need a multiplication symbol between them because they're just, when they're touching each other, that means multiply. And on the right, we have VFinal minus VInitial. So that's exactly what we did with this algebra problem on the right. We just had a 3 on the bottom, and we just multiplied by 3 on both sides. Without writing those steps, that's what we did. So now we have to still get the VFinal by itself. And so can someone else tell me how we can get the VFinal by itself? Danielle. If you're talking, I can't hear you. Do you have your mic on?
I'm sorry, I keep doing that. Add the VInitial to the
yeah. Exactly. We're going to add VInitial on both sides. And so we have VInitial plus acceleration times time equals VFinal. And it's kind of customary to rearrange this and put the thing we're solving for on the left. So I'm just going to flip the sides. VFinal equals VInitial plus acceleration times time. And this is our first master equation. Okay, I will refer to these as the master equations throughout the semester. And this is the first one that we learn. This is what this equation says. It says, take any object in the universe, any object, and tell me what its initial velocity is. That means its velocity at the time when you reset your clock, or suppose you take video footage. At the moment you start recording, what was its velocity? What is its acceleration? And what time do you want to know? And I will tell you how fast it will be going. I can even tell you how fast it was going in the past by putting in a negative time. There's no problem with negative time. That just means the time before we started recording. And this equation is just as happy to tell me how fast it was going yesterday as it is to tell me how fast it's going tomorrow. So we don't have to take final exactly so literally. However, usually it's confusing for us to, ask the question about yesterday. So you can think of this as always the final velocity. So we're going to get some practice using this equation, but let me just give you an example of a word problem where we would use this equation. Maybe we have a ball that starts from rest and it rolls down a ramp with an acceleration of 3 meters per second squared for 5 seconds, and I want to know how fast it's going at the end of that. So again, in English, we would say a ball starts from rest, it rolls down a ramp with an acceleration of 3 meters per second squared for 5 seconds. How fast is it going at the end of that? So our job is to read that English or hear that English and translate it into a series of mathematical sentences. That is the key to solving word problems. I really wish I could just teach before anyone took this class a 1 credit hour how to solve word problems course, because it would make such a difference. Raise your hand if in your math class the word problems was your favorite part. I'm hearing crickets. Maybe they're in my basement. Raise your hand if you don't like word problems that much. Exactly. And unfortunately, the only part of your math class that was useful at all is word problems, because almost nobody in the world just gets paid to solve math problems. What happens is you work for a company and they say, we've got this problem, our budget is over, and if we reduce the cost of this unit by 5% and increase the production of that, what's going to happen to our bottom line? You get presented math problems in English. And what almost all of us are really bad at is reading English and figuring out what is the math problem I have to solve, even though you mostly have spent probably at least 12 years of your life solving math problems. You spend almost no time solving English problems using math. So again, the word problem said a ball starts from rest. So when I hear or read the words starts from rest, I have to translate that into a mathematical statement. And the way I would write that is V initial equals 0. That's what starts from rest means if I translate it into a mathematical statement. A mathematical statement is an equation, something equals something, or an inequality, something is greater than something or less than something. Okay, it starts from rest and accelerates at a rate of 3 meters per second squared. That's pretty easy to translate. A equals 3 meters per second squared. And we'll talk about why the units of acceleration look like that in a minute. And it does this for 5 seconds. So that would be t equals 5 seconds. And the question is, what's its velocity at the end of that? And we would write that as v final equals question mark. Okay, so once I have translated my English problem, it is now a math problem. I don't have to look at the English problem again. I don't have to like read it and try to read between the lines. And you know, this was an easy problem, so maybe we don't need to go through this process, but it's good to practice this process on easy problems so that when the problems are too hard for us to figure out, we have a method to solve them, to attack them. So once I do this, I look at my list of equations. My list of equations is only one equation. And I say, well, can I use that equation, or can I find the equation that relates these quantities? So I would go through, if this were, you know, later in the semester when we have lots of equations, I would go through my equations and I might see this one and think, hey, that looks like a likely candidate. Do we know V initial? You know, V initial is in the equation. Do we know it? And I say, oh, we do know it. So I'm just going to underline the things we know in red. Do we know the acceleration? Well, I look at my mathematical translation. I say, oh, we do know acceleration. Good. I'm just going to underline that. Do we know the time? Yes, we do. Okay. And we want to know V final, and V final does appear in this equation. And then I just have to make a really quick judgment. Does this equation look like a good candidate to solve my problem? And yes, it does, because we know everything in the equation except for the thing we're looking for. So we can just plug in our numbers because the equation is already solved for V final. It says V final equals some stuff. If we were solving for time, I would want to rearrange the equation, get t isolated, and then plug in numbers. And again, we'll see a lot of examples of that today. But for now, let's just solve this problem. We have 0 plus 3 meters per second squared. I like to use parentheses once I start throwing units in to kind of visually guide my eye a little bit, times 5 seconds. And in terms of the units, the seconds in the time cancels one of the seconds in acceleration, leaving me with just meters per second, which is exactly what I want if I'm solving for V final. And so we get V final equals 15 meters per second. Now, as we go, most of the time I don't always write the units in when I'm solving problems, because you have a guarantee that if you're using the metric system and you use the base metric unit for each quantity, so I make sure that my V initial is in meters per second, my acceleration is in meters per second squared, my times are in seconds, that whatever we're solving for, it will automatically be in the correct unit, just like this was automatically in meters per second, which is the metric system unit of velocity. So we'll see it with units a few times, and once we feel comfortable, we may just leave the units off. And I would advocate leaving the units off unless you're having trouble. Then put the units in, and sometimes if they don't cancel properly, that lets you know you forgot something. Okay, any questions about this example? All right. So I want to do the same, what we just did with acceleration, using the definition of acceleration to create a master equation. I want to do the same thing with our definition of velocity. So our definition of average velocity is delta x over delta t. That's the displacement over the time. And in this case, we're not going to make an assumption that our average velocity is always constant, because that's too limiting. I mean, almost nothing just moves at constant velocity. So we're going to imagine our velocity could be changing. And we're going to try to rearrange this and solve for the displacement. So I want to solve for delta x in terms of initial quantities. So to solve this for delta x, hopefully it's pretty clear we want to multiply both sides by delta x. And when we do that, we will get, sorry, by delta t. When we multiply both sides by delta t, we will get delta x equals average velocity times delta t. And I'm going a little bit faster here. I kind of doing two steps at once. I'm multiplying both by delta t, which essentially moves the delta t to the top on the other side. And I'm also switching the sides. And that's probably more the rate that we want to be able to do our algebra. Now, for average velocity, we want to know how that's related to the initial velocity. Now, suppose you took two tests and you want to know your average grade. To find the average, you would add the two scores and divide by 2. So to find average velocity, we're going to add the initial velocity plus the final velocity and divide by 2. Now, technically, this is only true if the acceleration is constant. Okay, let me draw a graph to demonstrate that. Position versus time. And if I have a straight line segment, so that is constant acceleration because it has a straight line, then hold on. Let me, that's a 0 acceleration. It's constant, but I want something like this. So it has a curve, and we have an initial velocity and a final velocity. And what I'm saying is, if this curve has a constant acceleration, then the average velocity winds up being sort of the halfway between the initial velocity and final velocity. So we just find the average of those two. If this curve is kind of doing something like this, it would not be accurate to say this. Okay, but in our class, as I said, we're going to always assume the acceleration is constant. And so this is exactly perfectly correct. So our delta x, if I substitute average velocity for this expression, v initial plus v final over 2, and then we multiply by delta t, which is t final minus t initial, but we're the same thing that we did before, where we, instead of t initial, we put 0. We start our clock at the beginning. And instead of t final, we're just going to call it t. So the equation looks like delta x equals v initial plus v final over 2 times t. Any questions so far? Okay, so this is a perfectly good equation. However, what I want to do is I want to solve in terms of initial quantities, and v final is not an initial quantity. What I'd like to be able to do is make this an equation that predicts the future. You tell me the initial stuff and what time you want to know, and I'll tell you what the displacement is going to be. So in order to do that, we're going to use the equation that we just derived for v final. If we go back to the previous slide, we have v final equals v initial plus a times t. So I can put that in here, v initial plus a times t. And now we just really want to simplify. So to simplify, what I can do on the top, I put these parentheses here again just to help us see, you know, that what was VFinal becomes this expression. But you don't really need those parentheses from a mathematical standpoint because we're just adding stuff together. So when I have VI plus VI, I get 2 VI. And then we have A times T. All of that is over 2 and times on the outside of the fraction times T. And remember, if something's out of a fraction, and we multiply it onto a fraction, it goes onto the top. So we can think of this T as being really like T over 1. Okay, so the T is going to go onto the top. Now I want to keep simplifying. And the first question is, can we cancel the 2's? Raise your hand if you think we can cancel the 2's. Raise your hand if you don't think we can cancel the 2's. Okay, a lot of people say we can't do it. Someone tell me why we cannot cancel the 2's. You guys were pretty sure a minute ago. Katerina.
We can't cancel the 2's because we're also dividing the AT by 2.
Yeah, exactly. The AT doesn't have a 2. So we could only cancel the 2's if we could factor a 2 out of the whole numerator, which we can't do. So here's what we can do. Let me make a little line just to separate visually the space. We can split this fraction into 2 pieces. Still times, T over 1. And on the first fraction, we can cancel the 2's, but on the second one, we cannot. So we get delta x equals v initial plus, I'm going to rewrite this as 1/2 AT because sort of thinking forward to the final way we want to see this equation. And all of that is still times t. I don't have to really write t over 1 anymore because it's not confusing. I mean, I didn't really have to write it, but I'm trying to remind you how to work with fractions a little bit. But when I multiply a t times a 1/2 AT, I'm not confused the way I might have been confused here. So the final step would be to distribute the t. The t has to move on both of those pieces. So we get v initial t plus 1/2 AT squared. And this is our second master equation. And this is a really awesome, powerful equation. This equation says, tell me, for any object in the universe, tell me its initial velocity. That is, tell me how fast it's going when you start paying attention, its acceleration, and what time you want to know, past or future. And I will tell you where it will be relative to its starting point. That's what delta x is. How far is it from its starting point? Any object in the universe. And this is particularly easy to do right now during the pandemic because I can almost guarantee for most of you your delta x is just 0 because you're just sitting there in the same place all the time. But, I know some of you are going to work and, whatever. But at the end of the day, your delta x is still 0 because you got out of bed and then eventually, hopefully, you went back to bed. But this is a very powerful formula if you think about it. Just we have any object. We know its initial speed, we know its acceleration, and we pick some time in the future or the past, and we can tell where that object will be. In fact, this would be a very scary equation if it weren't for the fact that there's one limitation on this equation. There's one kind of bit of fine print that says it doesn't really work for every object in the universe. And that fine print is that we have assumed that the acceleration is constant. So for us personally as humans, we don't usually have constant acceleration. And so people can't really use this to predict our location, which is they have to track your cell phone to predict your location. Okay, any questions about master equation number 2? Okay, so let me show you what we have now. We have 2 master equations. I usually like to write the delta x equation first, even though we derive it second. Delta x equals v initial t plus 1/2 at squared, and v final equals v initial plus a times t. So those are our 2 master equations, and we can solve huge array of problems just using these 2 equations. Now, by the end of class today, we are going to discuss a third master equation, a third equation that will join us, and that will form our complete set of master equations. But I'm going to give you an extra credit assignment to create that third master equation on your own with some guidance from me on how to do it. So we'll see that at the end of the class. Now, before we take a break, we're going to take a break soon, but I'd like to try to pick a textbook problem from the 3000 Problems book and try to use the book or use those equations to solve the problem from the book. So we are going to do problem 3.9. I'm just going to keep those guys boxed. Okay, and we're doing the 3000 Problems number 3.9. So if you have your book, you should get the book out and look along with me. I will read it out loud, but it's better if you can look at it. And what we're going to do is we're going to do this in painstakingly slow detail because I want us to work on translating English into math. That is, if you can master that, you're going to have a much easier time in this class. So it says, a truck starts from rest and moves with a constant acceleration of 5 meters per second squared. So somebody tell me one math statement, one math sentence that I can use that translates part of that sentence. Danielle.
All right, can you repeat the textbook
Yes.
page number?
It says a truck starts from rest.
Sorry, the page number and the problem number.
Can you not see it up on the screen here? It's 3000 Problems book number.
Oh, I can. I'm sorry.
It's problem number 3.9. That's on page 37.
Okay, thank you.
Sure. Okay. So a truck. Someone tell me one math sentence. There's 2 math sentences in here, but someone tell me one of them. Something equals something. That is a translation from English into math for this sentence. I can't tell who just. Wyatt, is that you who raised your hand?
It was.
Okay. What's a math sentence we can get out of this?
A equals 5 meters per second squared.
Exactly. A equals 5 meters per second squared. Okay, someone else tell me another math sentence we can get out of the English. Isabel.
Time equals 4 seconds.
Oh, you're right, but that's in the second sentence, and I still want to go in the first sentence. Can you see anything in the first sentence, another math sentence we could write? Or can anyone else see that? Isabel, did you want to say it?
No, it's okay.
Okay. Grace?
Does initial velocity equal 0?
That's a question. I want to know a statement.
The initial velocity is 0?
Okay, that's good, but that's still a statement in English. I'm being a little picky here. I want a math statement. So I need to know exactly the symbols that I write down on the page.
So like VI equals VI is 0 meters per second.
Equals. Yeah, I don't even want to use the word is. I want to banish the English language from our problem solving. And I know that sounds silly, it seems weird, but really we want to know exactly what we want to write down and get rid of the English language entirely. If we can do that, we're in really good shape. And when we find we can't do that, it usually means there's something that we're not 100% sure of. And I knew you were 100% sure of this, but I still want to write it down this way. Okay, second sentence. Find its speed and the distance traveled after 4 seconds has elapsed. So someone else tell me another. Isabel, you had said for the second sentence, t equals 4 seconds. And would anyone else like to add something else that comes from this second sentence of the problem? Find the speed and distance traveled. How do we say that stuff as math sentences? Wyatt.
The distance traveled would be the delta x equation, right?
Okay, you're still speaking English to me though. I need to know
The delta
math
x equals
symbols to write.
delta x equals initial velocity times t plus 1
Well,
half.
okay, it equals question mark. So what I'm doing here is just translating. What you're trying to do is solve the problem, which is good, but I don't want to do that yet. So I'm just translating. And I know this seems picky, it seems nitpicky, but this is really important because as the problems get harder, we won't know how to solve the problem. So we want to learn how to translate it first, so that then we can think with sort of a picture of what we know in front of us in math, how to attack it. So delta x equals question mark. I'm just translating. It says find the distance traveled. That would be delta x equals question mark. And find its speed. That would be, it looks like it would be VFinal equals question mark, but technically it would be the absolute value of VFinal. That is the magnitude of VFinal. Because remember, speed and velocity are not exactly the same thing. The speed is how fast you're going. The velocity is a vector and includes a direction, which right now, that direction really can just be a positive number or a negative number. Our slope can be positive or it can be negative. But the speed should only be positive. Okay, so that's, again, just to help us, we need to translate this English perfectly so we know what's being asked for. Now, once we have done the translation, we go and we look at our first question, delta x equals question mark, and we look through our equations and we say, you know, which equation looks like the best equation? And obviously we only have one equation with delta x. So that's the one we should choose. So now we're ready to solve. Delta x equals v initial t plus 1/2 at squared. And again, this may seem like an unnecessary step, but it's really good to do this when the problems are easy so that when they get hard, we know how to proceed. I go through these variables one by one and I ask, you know, do we know v initial? Do we know it? Do we know v initial? Anyone? We do know v initial. Caitlin?
It's 0.
Exactly. We know it, and we don't have to look at the English anymore. You don't even have to have the textbook. I can rest my arm and put my textbook down. I do know it, and because it's 0, this is the only time I would put a number in. If I notice something 0, I'll cross it out, because if it's 0, it's going to not only be crossed out, but anything attached to it's also going to disappear. So I don't even care about this t. Do we know the acceleration? Raise your hand if you think we know the acceleration. Okay, we do know the acceleration. Do we know the time? Raise your hand if you think we know the time. Okay, we know the time. Do we know 1/2? Raise your hand if we know 1/2. Oh, you guys are so good. Okay, so we know everything. We know 1/2, we know A, we know T, and this first piece canceled out. So that means this equation works. And again, we only have 2 equations, so we're pretty sure this has to work. But as the semester progresses and as we have more and more equations, you know, there's a lot of choices, and so this process becomes more important. So delta x equals, I can now plug in my numbers, 1/2. My acceleration is 5 meters per second squared, and the time is 4 seconds, and we have to square that time. So when we square the time, the units of seconds also square. So this becomes a second squared and cancels the second squared that come out of acceleration, leaving me with only meters for my units. And let's see, 1/2 times 5 times 4 squared is 40. It's probably a good idea to have your calculator out when we're solving problems and, you know, test my math, because I don't have a calculator here. But I think that's right. Anybody get that with your calculator? Lena got that? Okay, great. So that's delta x. Now we want to find VFinal, and we go to our exhaustive list of equations and say, does anything have VFinal? Yes, the second one has VFinal, so we'll pick that one. VFinal equals V initial plus A times T. And then we test. Do we know V initial? Well, yeah, we saw we know it, and it's 0, so I'm going to cross it out. Do we know acceleration? Yes. Do we know T? Yes. So can we solve? Yes. Again, we're going to get today to problems where the answer to that question will be no. And so we need to, we need to see how it works when it is easy. So VFinal equals, now I'm not even going to write the units in. We just have acceleration, which is 5, and time, which is 4. So that is 20, and the units should be meters per second. If that doesn't kind of click with you, you might want to make yourself a little table of the different quantities that we learn about and what units they should have, because we want to internalize that if I see a velocity, the units better be meters per second. If I see a time, they better be seconds. If I see a delta x, it better be meters. If I see acceleration, it better be meters per second squared. And when you know the units, it makes it that much easier to interpret the English of the problems. All right, so this was a very, very simple problem. And I spent way too long solving it. You could solve this problem in much less time, but I'm trying, it's not just about this problem, it's about learning a system to approach solving problems so that when the problems get hard, you can rely on your system. I mean, that's how all of our society works, right? Almost everything is too hard for us to do. So we develop tools and we develop an algorithm, a system to attack it so that we can rely on the system. And we learn the system for easy things first, and then we apply it in harder situations. Okay, any questions about this problem? Okay, let's take a 5-minute break, and then we'll do some more problems. Ending the recording. Help me remember to turn it back on.